Hello, welcome everybody to the Energy and Sustainability Community of Interest webinar for February. Thanks for joining us again for another, what I think is going to be very informative and interesting webinar. We had a great turnout last month for the first webinar of the year, and I'm really excited to see how many we ultimately have calling in today. Our registration numbers indicate that this could really be one of our most popular webinars in a long time, so I'm excited that we're getting the word out to a lot of folks. Quick introduction. My name is Matt McCann. I'm a retired Navy Civil Engineer Corps officer. I had a heavy focus on facilities management and energy efficiency management during my Navy career. And I joined AECOM when I retired from the Navy about 6 years ago. I'm currently our federal energy market sector lead, and I have a leadership role in the SAME, Energy and Sustainability, COI, as you might imagine. I run the webinar program. Let's get some of the administrative stuff out of the way. Hopefully, if you're joined, but sometimes folks have trouble joining through the VPN. So if at all possible, if you may need to turn off your VPN to join clearly. If you're having trouble connecting audio, you may not hear what I'm saying, but hopefully you can see the instructions for troubleshooting here. If you have any questions, hopefully you have some questions. I think the presentation is really going to generate a lot of interest. Please post them in the Q&A tab. Let me just make sure, does it actually say Q&A? In the Q&A tab, you can use the chat for sharing anything else, but I will go to the questions, the Q&A tab to pull audience questions when we get there. Feel free to use the chat to post your name and where you're from if you're interested in sharing. And as usual, the recording started right at the top of the hour. So we are, if you have colleagues who weren't able to join, you'll be able to share the recording with them when it's posted. A little bit update on the COI. As always, if you're interested in serving on the committee, please send Michelle a note. We're always interested in getting more volunteers. Even if you don't know exactly what you want to do, reach out and we'll find something for you to help on. We had our monthly COI leadership call on Tuesday this week with really the biggest turnout we've had in a while. So I think it's an encouraging sign that the people are out there, are interested and want to get involved. Couple upcoming events. The next webinar is actually in April. We don't hold one during when there's national SAME events, so there's not one in March because of Capital Week. But the April webinar will feature ASHRAE Task Force on Building Carbonization. It's going to continue this year's kind of general topic for the webinars in this COI that align with the administration's priorities and goals, including those laid out in Executive Order 14057. Infrastructure bill funding impacts, vehicle electrification, advanced water conservation topics, carbon capture technologies, and others. I think we have a really good program lined up for this year. Also, you can see Capital Week coming up in March, JETSI in Denver in May, and links to both of those pages are here. I don't see the JETSI link in there, but we'll make sure to get that out to the COI. And one last administrative item, we like to do a poll when we start all of our webinars. So I think Rob is going to start the poll here. So please just participate here so we get a good idea of who is joining us for this webinar. So to the main event. I feel really lucky to have landed such a great slate of panelists today. Two of the folks at NASA leading the charge in understanding the science of climate change and educating policymakers on impacts and actions. Cynthia Rosenzweig and Sanketa Kadam are from the NASA Goddard Institute for Space Studies. Cynthia is a senior research scientist where she heads the Climate Impacts Group. And she has a long resume of really impressive things, including having been the co-chair of New York City Panel on Climate Change. She was one of the lead authors for the fourth assessment report of the Intergovernmental Panel on Climate Change, which we'll talk about the most recent one on this webinar. She's the co-director of the Urban Climate Change Research Network. And in 2012, she was named one of Nature's top 10 people who mattered. Sanketa Kadam is a research scientist at NASA Goddard in the Climate Impacts Group under Cynthia. She has a master's in climate and society from Columbia. Her research expertise includes climate modeling, impact modeling for decision making, and remote sensing data for adaptation. And her work encompasses climate variability, impacts on agricultural food systems, urban systems, and ecosystems. So with that, very impressive group here. Cynthia, please take it away. Oh, you're still on mute. Oh no. There we go. Yes.
Okay, great. Thank you. Sorry. Thank you, Matt, and thank you to the Society of American Military Engineers for inviting Sanketa and me to share some climate change basics in the seminar and the webinar today. We're from NASA Goddard Institute for Space Studies up in New York. That's where we are. So now I'm going to full. So we're going to tag team in our presentation today. I'm going to start off and give some climate change basics. We call that Climate 101. Then Sanketa is going to share latest findings from the Intergovernmental Panel on Climate Change, known as the IPCC. Their sixth assessment report was released last year. That's the real up-to-date latest science about climate change assessment done by scientists from all over the world. And then we're going to share, to finish up, tell about the program that Sanketa and I are working on within NASA to enhance NASA's resilience. It's called the Climate Adaptation Science Investigators Work Group. It's called Qazi, so that's from now on you're going to hear it called Qazi. But we want to share what NASA's up to in regard to enhancing resilience. So here we go, climate change basics. First, what's the difference between weather and climate? So we all know the weather. It refers to what we have right now that occurs locally over short periods of time, from minutes to hours, days to weeks. And of course, we know with the rain and the snow and the clouds and the winds and the thunderstorms, that's our weather. Climate, on the other hand, refers to the long-term regional or global average of temperature, humidity, and rainfall patterns over a period of time, often 30 plus years. So on the left, we have satellite data, satellite image of a storm over the Northeast. And on the right, we have, that's on the weather side. On the right, we have seasonal temperature outlook, looking climatically at what are the projections for longer term weather that's part of the climate as opposed to the weather. So with those two distinctions in mind, here's another thing that people often ask. In the beginning, often climate change was called global warming, but then we've now evolved to use the term climate change more. So what's going on with that? So global warming is the monotonic long-term heating of Earth's climate system that has been observed since pre-industrial period. That's approximately starting between 1850 and 1900. And this has been linked to human activities, primarily fossil fuel burning, which increase heat trapping greenhouse gas levels in the Earth atmosphere. We're going to look at that a little deeper. When you look at the graph below here on the lower left, you see this real very significant warming starting around in the 1960s, but in 1980s also, this true increase that's called global warming. Climate change is, again, remember, climate is the long-term change, 30 plus years, in the average weather patterns that have come to define Earth's local, regional, and global climates. So climate change encompasses the global warming that we're looking at in the left-hand graph, but it refers to a broader range of changes in other climate variables that are happening to our planet. And we're going to be looking at some of those as well. But first, let's step back and consider the radiative basis of our planet and what's going on with the sun and the Earth, and with a stop to the moon on the way. This is the radiative basis of climate change. So, when there is warmer temperature, more energy is radiated away. First of all the energy comes from the sun. Those are the orange arrows on the left, warming up our planet. In the moon, as you can see, has virtually no atmosphere. So there's no gases around its surface. And so the energy coming in from the sun equals the energy going out. At the Earth, the same rule, radiative balance rule, applies. Energy in has to equal energy out. But we have an additional atmosphere, which is thickened by not only the greenhouse gases, carbon dioxide, methane, and nitrous oxide, which absorb long-wave radiation, but also water vapor is part of our atmosphere as well. Sometimes I describe this as a kind of gaseous blanket. So we still have the same amount of sunlight coming in, but some of the outgoing long-wave energy is trapped. So our energy in is greater than the energy out on Earth. Therefore, in order to maintain the radiative balance of the planet, the surface must warm to get back to balance. And that means that now our energy in and our energy out is equal. This is why, even before we had increases in the greenhouse gases, carbon dioxide in particular, our planet is warm enough to sustain life on Earth. But what we're doing now through the increasing in greenhouse gases is we're augmenting our planetary warming that we are re-radiating back to space. Now, when we think about the factors, so far we've mentioned the greenhouse gases and water vapor. Natural processes, we're going to look now at what are the factors that can cause climate change, changes in that radiative balance. So the first is natural processes that can contribute to climate change, including internal variability. So these are large climate patterns, variability patterns like the El Nino and La Nina, which are cyclical ocean and actually associated atmospheric patterns, as well as those are internal to the climate system. But then we also have external forcings. So when volcanoes go up, here we have the Tonga eruption, just that happened recently. Those clouds, those billowing clouds, are sulfate aerosols, which then go up to the atmosphere. And they, on the other hand, scatter sunlight and cause cooling. There's also changes in the sun's energy output and variations on the long term in Earth's orbit. So these are the natural processes that can change climate. But we now have human factors as well. Changes observed in the Earth's climate, remember we looked since about the early 20th century, are partly driven by human activities, particularly fossil fuel burning. This is coal, oil, and natural gas, and deforestation, because cutting down trees for agricultural land to create agricultural land releases the carbon that had been stored in the trees in the soil. So both of these activities increase heat trapping greenhouse gas levels in the Earth's atmosphere. Remember our planetary radiative balance that we just looked at, raising the Earth's surface temperature. The Now we've been looking just so far in recent times in Earth history, maybe up to a couple of hundred years, but uh, our paleoclimate colleagues, scientist colleagues, look way back in Earth's history, and that's what this graph is showing. That the Earth's climate has changed continuously throughout its history, and in the over the last 650,000 years, there have been 7 cycles of glacial advance and retreat, warming periods and cooling periods. And we can see that there was just most recently, so you see those ups and downs. So the ups are the warm periods in Earth's history are associated with higher levels of carbon dioxide, and the cooler ice ages, the colder periods, are associated with lower. And this has to do with what is going on with the greater vegetation and the vegetation cycles happening during the warmer periods. But here's on the far right of this graph, we can see what we were just looking at on the paleoclimate Earth's history time scale. And the current warming trend is of particular significance because it has been accelerated by human activity, especially since the mid 20th century. Our last ice age ended about almost 12,000 years ago. And that, by the way, that marked the beginning of our modern climate area and human civilization and the development of agriculture, by the way, which is one of the foundations of our civilization that really began to occur about 10,000 years ago. So that's in our past. Now we're going back up to 1980, and what's going on with these? What are the increases of not only carbon dioxide, but also the other greenhouse gases, methane, nitrous oxide, and the CFCs are also those man-made gases are also greenhouse gases. So, how are these linked to the warming that we've experienced? The planet's average surface temperature has risen about 1.8 degrees Celsius. I'm not going to read the Fahrenheit since the late 19th century. And this change, as we've been saying, largely driven by the increase in greenhouse gases that are shown here. And these are caused by the IPCC has said unequivocally, and you'll be hearing more from Sanketa shortly about the IPCC and their statements about the human influence on the climate. And most of the warming has occurred in the past 40 years, with the 7 most recent years being the warmest. And one of the reasons for this, why has there been the significant increases more recently, is that the greenhouse gases have really been you can see rising, and it's those additional ever increasing levels of carbon dioxide and methane in the atmosphere are causing that planetary effect of the warming to occur. Now, we've been looking only primarily up until now at the rise in global temperatures, but as we can think about our whole climate system, there are other effects that we're seeing as well, and there is evidence of rapid climate change, not only in the global temperatures, but in the warming oceans, in sea level rise, shrinking ice sheets, and extreme weather events. So it really is the whole set of the elements and components of our climate system. Now, one of the evidence of rapid climate change is occurring all over the world, and there are hotspots, what we call hotspots or tipping points that scientists are taking a very close look at and watching very carefully, because a tipping point is the point at which small changes become significant enough to cause a larger, more critical change that can be abrupt, irreversible, and lead to cascading effects. So there are changes in the Amazon rainforest, Arctic sea ice. We're going to tell a little bit about that in a moment. Atlantic circulation, that's how our Gulf Stream may be changing. The boreal forest, where fires and pests can be changing. The Amazon forest can be very much linked with the deforestation there to increasing droughts. Coral reefs with large-scale die-offs. Both the Arctic sea ice and the Greenland ice sheets are accelerating. And permafrost thawing that could lead to great emissions in methane that are stored there. West Antarctic ice sheet, and also other changes in the Antarctic. So these are these hotspots that climate scientists and NASA scientists, a lot with the remote sensing, are just really bearing down on keeping track of what's going on with these tipping points. Just to give you one example of why they're the topic of so much interest in scientific interest and societal, is that, for example, the Greenland ice sheet melting, if it were to melt completely, which of course is uncertain, but if it were all to melt, then it could add up to 7 meters to sea level rise. And current projections are more like on the order of 1 meter, while West Antarctic ice sheet melting could add up to another over 3 meters. So these are why the scientists are keeping close watch on these tipping point hotspots. Now, I mentioned the climate system. So we've been focusing primarily on the temperatures. We've looked at a range of gases in the atmosphere. We've looked at the solar radiation. But there's so many parts of the climate system, including what's happening on the land with vegetation and soil interactions, what's happening with the oceans. We've talked about these with some of the tipping points, the cryosphere. We talked about the volcanoes going up, and we talked about the human contributions and responses. So, well, we're getting to the responses at the end of the talk. So how do we study all of this? How do we put this all together? And what we do is we create mathematical models of the climate systems. And so we are here at GIS. We are the home of one of the, what's actually one of the oldest global climate models that is used to study the climate system. The models are built on principles of physics and chemistry. They're balanced across the water and energy budgets. They start with initial conditions and boundary forcings, such as sunlight, land use, change, and greenhouse gas emissions. They use surface station data and remote sensing data sets to improve to set and improve the parameterizations and develop the parameterizations. And then they are independently validated against observed trends and variability. We're going to look at a little bit of that shortly. And because of the validation, they are then used to extend beyond observed conditions. But no model is perfect. I'm sure as engineers, you all know that. They're subjects to limits and predictability, given the chaotic nature of climate change. Not everything can be modeled, but they have been proved to be useful tools for projecting changes, in particular in the radiative forcing, at the effects of the radiative forcing that we talked about when we looked at the radiative basis of climate change. Now, they're constantly working to improve them, and with enhanced computer power, the resolution over which the equations are resolved and are solved is constantly getting finer and finer. There are also a set of models that with very fine resolution do look at regions, for example, but with the coasts to look at key processes such as sea breezes, ocean land breezes, for example, and then elevation, where a big grid box really just wouldn't be able to get the fine level granularity that's needed to simulate the processes. And then empirical models are used also for downscaling as well, based on observed climate, right, in right in our own area. So this is looking at Europe and how it's represented in the models with the Mediterranean. Okay, I want to give two examples of how these climate models are used. First of all, they are used to determine the human influence on the climate system. What the graph is showing is change in global surface temperature, the annual average, both the observed, that's the black line, and simulated using two different sets of inputs. One is using only the natural factors, that's the green line and the green range around the green line. The other simulation experiment was used with both the natural and human changes in the greenhouse gases. So the natural variability, remember, the volcanoes are put in, the solar cycles are put in, the changes in the axis and orbit are put in. But it's only when the climate models are used, are input with human factors, the greenhouse gas emissions, the aerosols, remember those are the cooling, and then the land use change, which also changes the reflectivity of the earth. Then and only then can the models actually replicate the observed changes. Remember, and that significant change that we've been seeing in the last few decades. So it's because of this simulation experiment that the human influence on the climate system is determined. Now, that being done, then the second use of the models is to project into the future. So how do we do that? Because we don't know the future, right? So it's the way that it's done is that it's with a set of scenarios, and these scenarios are called the SSP and the RCP scenarios. SSP stands for shared socioeconomic pathways. These are the things in the future that may happen in regard to income, in terms of technology, in terms of land use, and in terms of governance. The RCP stands for the representative concentration pathway, which are the physical aspects, the greenhouse gases, aerosols, and carbon fluxes. And the scenarios are fed into the models. And now you can see on the graph on the left, remember the black line is the observations. They are all following, of course, they're following the historical patterns. But then with the different SSP, RCP combinations, they produce a range of future projections. They're represented, we call that the fan diagram. And that's over time. And then the one on the right is looking in particular at for each one of the SSPs, what the temperature change and the range is projected. Now, just to go a little bit further in what these SSP RCP storylines are, because this is really group work to develop these SSPs, a community effort to test how a useful set of possible futures. So the first one could be called the sustainability scenario. And here these are called storylines, taking the green road. So this scenario envisions relatively optimistic trends for human development with substantial investments in education and health, rapid economic growth, well-functioning institutions. There's an increasing shift towards sustainability, and I know many of you're in the sustainability group at SAME. And the stabilization pathways of the greenhouse gases, in which the radiative forcing is stabilized at approximately 2.6 watts per meter squared. And remember back to our radiation diagram that the radiative forcing is measured in watts per meter squared. The SSP2 4.5 is the middle of the road, in which these trends don't shift markedly from historical patterns. And there is some reduction in greenhouse gases, emissions, and radiative forcing, but it is not as, that reduction in the watts per meter squared forcing is not as high. And then the third one that we're using, and we're using with Qazi, and we can explain why later on, perhaps in the discussion, it's called regional rivalry, a rocky road. Here, their countries and regions are more focused on achieving energy and food security goals within their own regions, the expensive broader-based development, and I would say also at the expense of work on reduction of greenhouse gases. So that's how we make the projections, and here they are. So these are linked to global warming levels with utilizing the work of those scenarios. Annual temperature is on the left, annual precipitation is on the right. What you can see from this is the distribution across the whole world that occurs with these different warming levels. You see on the temperature side, high latitude warming, and of course in the 3 degrees world, significant warming across almost everywhere on the planet. On the precipitation side, green is for wetter, yellows and browns are for drier. Again, you see differing changes around the world, and with more extreme changes associated with the higher warming levels. So with that, now let's turn to Sanketa and delve into what the IPCC scientists have brought forward in the latest IPCC report.
Thank you, Cynthia. Yeah. So we're going to look at the IPCC in this section, which is the Intergovernmental Panel on Climate Change. And IPCC was created to provide policymakers with regular scientific assessments on climate change, its implications, what are the potential risks, and how we can adapt and mitigate those risks. So through its assessments, the IPCC determines the current and the most latest state of knowledge on climate change. It identifies where there is agreement in scientific communities, and it also identifies where future research is required. It's really a global framework, like Cynthia mentioned. It brings together scientists from all over the world. And the latest 6th iteration of the report was released last year in 2021 for the physical sciences, which is the working group 1. And let's look at what the key themes are from the report that came out last year. The first is we have the highest degree of certainty ever that the climate change is caused by human influence. And then we look at the detection and attribution of extreme events. And so detection and attribution simply means assessing the causes of observed changes in the climate system through systematic comparison of climate models and observations using various methods, and then attributing those changes in extreme events to human influence. In this report, adaptation comes to the fore at last, which means that the report really highlights the importance of adapting our adaptation policies today, because we're seeing the negative impacts of climate change right now in many parts of the world. And then we have also focus on regions in this report. And we look at all of these one by one. So highest degree of certainty ever that the climate change is caused by human influence. It is indisputable that human activities are causing climate change, making extreme events, including heat waves, heavy rainfall, and droughts more frequent and severe. So human influence has been the main driver of hot extremes, which have become more frequent and more intense. Ocean warming since the 1970s and ocean acidification has increased. We see changes in frozen areas of the planet. There's 40% decrease in Arctic sea ice since the 1979. So these are just some of the key findings from the report that have come forward. And to just look at some of the numbers to give you the sense of scale of the impact, there's been highest level of CO2 concentration in at least 2 million years we see sea level rise has been at the fastest rates in at least 3,000 years. Arctic sea ice is at the lowest level in at least 1,000 years, and the glacial retreat is unprecedented in at least 2,000 years. Another important finding from the report is that the projected changes in extremes are larger in frequency and intensity. We've had 21 named storms in 2021, with at least 8 of them that smacked the US coast and were very destructive. It was also the 6th consecutive year in which there was above average tropical cyclone activity. And the report also highlights that the global proportion of major, which is category 3 and 5 tropical cyclone occurrence, has increased over the last 4 decades. And the latitude where cyclone reaches peak has shifted northward. So we not only see an increase in intensity, but also frequency in extreme events like the tropical cyclones. And the last point that really is very important that came from the IPCC report is the focus on regions. And I want to just take an example and explain this table that is in the chapter 12 of the IPCC report. It really divided the regional risk matrix for the entire world, but this table especially focuses on the North America, and they have these risk matrices for each part of the world in the report. And so let's look at under wet and dry, the second column, you have the last one, which is fire weather. And what we see is in North Central America, we have high confidence that the fire weather is increasing. And the fire weather here really means the conditions that are conducive to having more frequent fires. And then we see in Western North America, we also have high confidence of increase with the numbers 6 and 7. And the 6 and 7 really means that there's higher confidence that the northern part of this region will have more fire weather activity. So it's really dividing the region into further spatial disaggregation. And then let's look at another example. Under the heat and cold, you have extreme heat. So we can see that the North Central America, Western North America, Central North America, and almost all of them have high confidence of increase in extreme heat. And the black dots really there mean that this has already happened. So in most of those regions, we've already seen extreme heat. And I think that's the last slide on IPCC latest findings, and I'll give it back to Cynthia.
In the last part of our presentation, we want to share what we're working on with colleagues at NASA to enhance NASA's resilience. And as we said, it's called Qazi, the Climate Adaptation Science Investigators Work Group. But what this before we delve into the specifics, we just want to also show this. It's called the propeller diagram from the IPCC Fifth Assessment Report, because what it is doing is really highlighting why are we caring about all of this. And it is saying that we need to be assessing climate impacts and the risks for things that we care about in terms of the hazards, the vulnerability, the exposure, the socioeconomic processes. We looked at that both on the impact side, the emissions and land use side, what's happening with natural variability, anthropogenic climate change, and what can we do about it? And how can we respond? Basically is the question. And both adaptation responses in terms of enhancing resilience to the impacts, and the mitigation also responses in terms of reducing greenhouse gas concentrations in the atmosphere, they also help to reduce the risk because it lowers, as we saw in the fan diagram, it lowers the amount and the rate of change in the amount of climate change that the planet would experience. So this mitigation again is that reduce, so 2 words basically for the responses: mitigation, reducing emissions of and stabilizing the levels of heat trapping greenhouse gases in the atmosphere; adaptation, adapting to climate change, already in the pipeline. Already, some changes, as we've seen, are all in from the IPCC report, are already happening and are projected to increase in intensity and frequency in the future. So, in regard to some of the things that NASA is doing, and I know all agencies, I believe, all federal agencies are required by the executive order to develop adaptation plans as well as mitigation plans. Um, so, just to share some things on, we'll do the mitigation first, then we'll go to the adaptation because that leads into Qazi. So, for the mitigation, one of the things is that's being done is to collaborate with federal partners and industry and other stakeholders to work on aviation solutions that can reduce emissions of carbon dioxide, the dominant aviation GHG. So this would be increasing um, the efficiency of the use of fossil fuels in aviation. And there are multiple energy consumption and efficiency projects that are going on, plus, and not all of them are only efficiency, but also then at NASA centers hosting solar photovoltaic systems for energy uses. So these are some of the things that NASA is working on the mitigation side. On the adaptation side, in the NASA Climate Action Plan, are to identify the vulnerabilities, develop risk reduction strategies, modernize all of the agency master plan to better integrate climate risks that we've been discussing, develop an agency resilience framework and center resilience plans, help to develop, this is on the science side, to develop climate change resilience, to develop the next generation of climate models, to expand the understanding of the Earth's climate and climate change, and to improve, of course, all the climate science and the GIS capabilities to identify and map acid level hazard exposure. So one of the things that is being done as part of the adaptation action by NASA is to develop Qazi. The mission is to provide the latest scientific research on climate change to help NASA facilities and the managers there adapt to increasing climate risks in timely and effective ways. And this is done by creating work groups which are made up of ESD, stands for Earth Science Division. Those are the climate scientists within NASA, and the OSI, which stands for the Office of Strategic Infrastructure members. So it's it may be the only program within NASA that is actually bringing together the scientists and the facilities managers together. So we have work groups, and we'll see that you see them on the right. And Sanketa and I and others at GIS are working on coordinating all this. So the work groups, which are, remember, both scientists and the facilities managers, are on the temperature and precipitation projections, extreme weather events, sea level rise and coastal flooding, fires and air quality, energy and water budgets. And so, as we said, we're downscaling center specific. So taking that fan diagram at the global scale, and then we're pulling out, and we're going to show a little bit more about that. We're downscaling for each center in the regions what the climate hazard information is projected across those SSP RCP combinations. We're creating Qazi work group products as decision aids. We're helping on the resilience assessments. We're advancing climate literacy through RSET training materials. That's also what we use as in part in this presentation. And then developing community outreach for the regions around NASA centers. So that's the Qazi activities. So to tell a little bit more about the Qazi projections, because this is one of the key products of Qazi, to provide observed and projected climate data for all NASA facilities. So we've made this as big as possible. You can see that these are the winter mean temperature changes this is for the 2050s, and all the black dots are where the NASA facilities are located. And so the top one is the winter mean temperature change projected, and the lower map is showing the mean temperature change for the summertime. And then we also provide tables, so that this is for Stennis Space Center in Alabama, where for the decades we provide low, middle, and high estimates, so that the managers there who are developing, let's say, this is for temperature, precip, and sea level rise. Let's say, for example, at Wallops, they're doing a sedimentation study, and they can then utilize these projections to learn about what the future changes in the sedimentation in Wallops Island may be. For example, that's an example of how these projections can be used. They're based on a wonderful NASA product called NASA Next, stands for NASA Earth Exchange, this is also all hooked up to the National Climate Assessment. And so we encourage you to check out the NASA Next website. And then we utilize these, and we grab from these and downscale for the centers, not just the temperature, precip, and sea level rise, but also min and max, as well as average, relative humidity, and we're doing radiation and wind speed, a kind of a basic set of climate/weather variables. These are the details, how we're doing them based on IPCC. It's all linked to the IPCC report that Sanketa just presented. The key part is that we're providing maps and tables and data, so that the managers at the centers can actually utilize the projections in their decision making. We're now doing them decadally, and we're doing them for the three of the scenarios that we were describing earlier. To give you a flavor of the workgroup products, just sea level rise and coastal flooding. What's the sea level rise projections? What are the high tide flood levels, extreme water levels, and coastal inundation maps? For the extreme weather event, work group is working on droughts and high temperatures and inland floods and how they may change, both separately and together. Because fire risk is such an important risk. We have a fire and air quality group that's looking at wildfire risk and smoke risk. And then we're working on energy and water budget for energy management tools and for managing the water at the centers as well. Key part is in the square on the right: co-generation, co-production. It's a form of knowledge production based on the dynamic interaction between the technology and the society. In this case, it's between the NASA scientists and the managers, where technical experts and of both science and technical experts and the managers come together to develop information and products. So we're not just making the climate scientists making these products and throwing them over the fence and, oh, here's some stuff that might be helpful. We're working with the folks who are actually going to be using them to try to make them, the products, as useful as possible. This is just to say we have all these amazing NASA, I'm sure you may have seen some of them, the amazing delivery mechanisms and platforms for NASA data. We'll be utilizing those, and they're going to be on them. The Qazi products will be on them. But we want to end now, and I hope we still have time for some questions from Matt and also the audience, to really put a suggestion out that perhaps we can develop some interagency collaboration in regard to shared projections, in regard to co-generated products, regional workshops, because many military, as you I'm sure are aware, many NASA centers and military installations are located in the regions, and we could hold some climate change risk workshops perhaps together, and maybe also turning over to Matt now about the questions and comments. Maybe we can also develop some FAQs from this presentation. Over to you, Matt.
Yeah, thank you. And I think the idea of kind of taking this further into an FAQs or trying to, develop joint, workshops or kind of leveraging your expertise and the knowledge and, need for these kinds of products from the industry and the folks who are listening in on this call from the federal government and other sources. I think it really aligns well with what SAME's vision of what the community of interests are all about. It's not just about having a webinar and moving on, but if something like this could really stimulate some further interaction and other people who can take advantage of the amazing work you're doing, I think that's exactly what SAME wants to do with this program. So thank you for really an amazing presentation. I hope everybody who's listening got as much out of it as I did, and through preparations of having opportunities to talk with Cynthia and Sanketa over the last few weeks. I wanted to pose a few questions. I didn't see anything in the Q&A yet, but please post there. I'm gonna start off with a few kind of moderated questions. But one of the things that's really interesting to me is this idea of the periodicity of storms, right? I think we all recognize that how often that we're talking about the 100-year storms are happening this year and have happened over the last 5 years or whatever. So how do we take that idea of, even on your chart, the 50-year storm that's going to happen, eventually 39 years out of 50? How do we as a society kind of take that and adjust what the definition of the periodicity of storms are?
I think, Matt, I think this is a great and very important question, and I think it's also very germane for our engineering colleagues. Because it's there's several federal agencies, including NOAA and FEMA and USGS, but also groups like the American Society of Civil Engineers to calculate those 1% storms. Let's say sometimes it's called 1 in 100, but it's really the 1% storms, right, over the period. And then say, you know what, we're changing now and we need to update our baseline and change what that level of the 1 in 100-year storm is, and change that level to be, oh, it's no longer the 1 in 100, it's the 1 in 50, it's the 1 in 10, right?
Right.
So this system it needs updating, and it's my understanding, but there may be some participants in this webinar who have worked with, for example, the ASCE, because I know they have a work group on this exact thing. So we're going to be looking to find out as well, because our NASA engineers will be also very interested in whether now these definitions, as the climate is changing, what is the process by which those guidelines and regulations and definitions for the extreme events are updated?
Right. Thank you. And, I welcome, input from, as Cynthia suggests, input from folks who are listening in who have more knowledge about that, about how that actually happens in real life. I have a question here from Michelle, the leader of the COI, and she, as I did, kind of really picked up on that idea that you can't deny the fact that the natural forces only chart just does not follow the reality of what we're observing in real life, right? But we have a political system that doesn't necessarily recognize the reality of what's happening or want to kind of put factors on it that don't follow the models and the reality here. Do you think that the more prevalence of this kind of data and education efforts from you and other climate scientists, is it lessening? Is there any trend of kind of understanding that there are less climate deniers now than there were last year, or is that anything that you follow within the work that you do?
Yes, we do follow that work. It's not the work that we do at NASA. We're working on, I'm at GIST today, And when all the scientists are here, but now they're all basically working from home, they're working on improving the models morning, noon, and night. That's, we NASA scientists really work on the science, but we certainly have colleagues. For example, there's the Yale and George Mason is one of the universities that tracks the perceptions of the science. And look, as we move into the response part, that we are now really that era, really, we're really moving into a time of responses, both on the mitigation side and the adaptation side. And so learning about and understanding what the perception of climate change is, how we can present it, and what we try to do is present it as clearly as possible, and share it as often as we can. So that's why we're also so pleased to come and share. And share this webinar with you.
I appreciate it. And hopefully your enthusiasm helps shape that message for folks who don't want to listen to the data. I have a question here from Steve Wershing, who I worked with in the Navy. Hi, Steve. How are you? He's asking if you can talk a little bit more about the progress with aviation. I noticed when you were talking about Qazi, you kind of mentioned the work with aviation. Presumably that means that's the kind of the biggest impact in the data and the changes that you're seeing in the models.
Yes, so I can tell a little bit about it. In Qazi, we're really working more on the resilience and adaptation side than the mitigation side. But I'll just tell an anecdote. A short anecdote. I attended the 26th Conference of the Parties of the United Nations Framework Convention on Climate Change in Glasgow. And one of the things you had to do was wait in these long lines to get, show your badge and also have your, show your vaccination certificate and everything to get in. And so I always use those opportunities to chat with the people around me. And I had a very interesting conversation with someone from the who was working on the aviation. And he said that this is on the commercial side, that they're bringing all the big commercial carriers together and working on getting commitments for early adoption to go to the lower greenhouse gas emitting fuels. And this is evidently what's happening in other sectors as well, that the sector is coming together and seeing what are the actual differences, issues, and costs, and then making a plan by which then the sector can move as a whole to the lower greenhouse gas emissions and the more efficient fuel. So we'll be finding out also exactly what NASA is doing, but I think that NASA is engaged with some of these energy efficient projects as well.
Something else in the work around Qazi that really caught my attention, and probably others as well, is this idea of your energy and water budget tools. I think that's really important as we kind of project. I think a lot of folks out there are involved in ESPCs or other energy projects that really rely on identifying what the potential savings are versus current budgets or energy costs. So what kinds of things are taken into account as you do that? And I especially think about on the water budget tool. Does scarcity of water in the future fold into what you're projecting for those tools?
So these tools are focused on the projected changes in the hydrological cycle with climate change. It doesn't include in other of our projects. We work with economists that it would include folding in the cost. But for Qazi, for NASA, right now we're working, and I actually, I think some of the facilities managers, as you're saying, they would be aware of the various potential changes in costs. What the Qazi climate scientists are doing are taking those downscale projections and seeing how the water resources For example, in Ames in California, with the watersheds up in the mountains, the potential for drought there, what the projections of climate change are really showing for center water resources and water use is both the sources as well as evaporative demand. So that's what we're doing. But by linking with our OSI folks, our facilities managers, they would, and Sanketa, let's check with them to see next time when we have our work group breakouts, to see whether they can bring in the cost part as well, which of course is crucially important, as it is with the aviation fuel as well, by the way.
Yeah, thank you very much. We're at the top of the hour. I want to thank you for your enthusiastic, informative, and really just interesting and fun presentation. Hopefully, like I said, the other members of the COI who are listening really got a lot out of it. If you have further questions, I don't see any more in the Q&A right now, but I'm happy to relay questions to Cynthia and Sanketa. If you have them, you can send them to me or through Michelle. And I really look forward to, as we talked about, perhaps furthering this conversation with a wider group of folks from the community who can help further the work that you're doing and allow us to leverage the work that you're doing as well. So thank you very much.
Thank you, Matt. Thank you, everybody. Yeah, looking forward to continuing interactions. Thanks so much.
Thanks.
Thank you, everyone. Thank you for having us.
Bye.
Bye.